Good morning, students. This is Latif sir. In this video, I am going to discuss about the calculation of packing efficiency in different type of unit cell. Okay. In the last video, I have already discussed about what is solid, types of solid, and types of crystalline solid, unit cell, crystal lattice. Okay. And I have told that there are four types of unit cells: simple, face-centered, body-centered, and end-centered unit cell. Okay, and there is total seven number of crystal system like cubic, tetragonal, hexagonal, like this, monoclinic, triclinic, like this. There are total seven types of crystal system are exist in nature, and we will discuss only about cubic crystal system. Okay, like simple cubic unit cell, face centered cubic unit cell, body centered cubic unit cell. Okay, so let's start this topic, packing efficiency. You have to remember that in simple cubic unit cell there are total one particle. There is only one particle per unit cell on an average, and in case of face centered cubic unit cell there are there are four particles per unit cell, and in case of body centered cubic unit cell there are two particles per unit cell. You have to remember this point. And now, what is packing efficiency? You know that in in crystalline state of matter, that is in solid state, the particles are very closely attached to each other. Okay, so particles are very closely attached. Okay, however there are some free space in the form of void. Okay, so in whatever way the constituent particles, that is atom, molecules, or ion, are packed, there is always some free space in the form of voids. And what is packing efficiency? Packing efficiency is the percentage of total space filled by the particles. Okay. Packing efficiency, you can see, packing efficiency is the percentage of total space filled by the particles, and mathematically it is calculated using this formula. Packing efficiency is equal to total volume occupied by the particles in the unit cell divided by total volume of the unit cell into 100. Okay, packing efficiency is the volume occupied by the particles per unit cell divided by volume of unit cell, total volume of unit cell, into 100. This is the formula of calculation of packing efficiency in different type unit cell. Okay, so first see simple cubic unit cell. Simple cubic, this is simple cubic unit cell. Okay, it look like this, and these are particles. Okay, and this is the unit cell. And you know, in case of simple cubic unit cell, the particles are present only at the corner of the unit cell, and there is one particle per unit cell in case of simple cubic unit cell. Okay, this structure, this is for simple cubic lattice, and this is calculation of packing efficiency of simple cubic cubic unit cell. And see that in simple cubic unit cell the particles are attached along the edge length of the unit cell. Okay, suppose this is an unit cell, simple cubic unit cell, and particles are attached along the edge of the unit cell. So if edge length of the unit cell is a, if edge length of unit cell is a, and radius of each particle is r, then you can conclude that In case of simple cubic unit cell, there A is equal to 2r, r plus r. Okay, so you have to remember that in case of simple cubic unit cell, the particles are attached to each other along the edge of the unit cell. So you can write A is equal to 2r. Here A is the edge of the unit cell, edge length, and r is the radius of each sphere, each particle. Okay, and in case of simple cubic unit cell, there is only one particle per unit cell. And now if A is the edge length of unit cell, uh, or it is also called edge length or side of unit cell or cube is A. If the side or edge length of the cube is A, then what is the volume of the cubic unit cell is AQ. AQ. If edge length is A, then volume is AQ. And we know that A is equal to 2R for simple cubic unit cell. So you can also write AQ is equal to 2R whole cube, that is 8RQ. This is the volume of unit cell. Okay. So volume of unit cell is AQ, that is 8RQ. And since a simple cubic unit cell contain only one atom, so volume occupied by one sphere is 4/3 pi rq. If the radius of each sphere, each particle is r, then volume of each sphere is 4/3 pi rq. So total volume occupied by one particle is 4/3 pi rq into 1, that is 4/3 pi rq. This is the volume occupied, or the volume of the occupied space is equal to 4/3 pi rq, and total volume is 8 rq. Total volume is 8 rq and volume occupied is 4/3 pi rq. So packing efficiency is volume of one in case of simple cubic unit cell, packing efficiency is equal to volume of one atom, one particle, divided by volume of cubic unit cell into 100. So volume of one particle is 4/3 pi rq and volume of unit cell is 8 rq. So 4/3 pi rq divided by 8 rq. Okay, and after calculation, the final result is 52.4%. That is, in case of simple cubic unit cell, for 52.4% space, or 52.4% of total volume is occupied by the particle, by one particle, in case of simple cubic unit cell. Okay, this is the simple cubic unit cell. Now see calculation of packing efficiency in case of face-centered cubic unit cell. One thing you have to remember, in simple cubic unit cell, 52.4% volume is occupied. Then unoccupied volume is 100 minus 52.4. 100 unoccupied volume is 100 minus total volume is 100%. 100 minus 52.4, that is near about 47.6% volume is available. Okay, that is unoccupied volume. Now see calculation of packing efficiency in case of face-centered unit cell. This is the face-centered cubic unit cell. It is also called hexagonal HCP or CCP cubic structure. Okay, HCP and CCP, these are also called face-centered cubic structure, or you can also say HCP and CCP means face-centered cubic structure. So packing efficiency in face-centered cubic structure. First you have to see the structure of face-centered cubic unit cell. You know that in face-centered cubic unit cell, the particles 8 particles are present at 8 vertex, 8 corners. Okay, 8 particles are present at 8 corners, and one particle at the midpoint of each faces. Okay, so on an average there are total 4 particles present in face centered cubic unit cell. And one thing you have to remember, that in case of face centered cubic unit cell, the particles are attached not along the edge length of the unit cell or side of the unit cell, but particles are attached along the phase diagonal of the unit cell. The phase diagonal is this one, is the phase diagonal. Okay, or like these are phase diagonal. Okay, these are phase diagonal. So in face centered cubic unit cell, particles are attached along the phase diagonal of the unit cell. And according to this face centered unit cell, cubic unit cell, the phase diagonal is AC. Okay, and if the edge of the unit cell is A, then phase diagonal AC is equal to root 2A. Okay, phase diagonal is root 2A. And if the radius of each sphere is R, then R plus 2R plus R, that is 4R, is also the phase diagonal AC. Okay, so you can write in case of face centered cubic unit cell, you can write 4R is equal to root 2A, because according to this cubic face centered cubic unit cell, the phase diagonal AC is root 2A, where A is the edge length of unit cell. And if the radius of each sphere is R, then R plus 2R plus R, that is 4R, is equal to AC. So you can also write 4R is equal to root 2A. Okay, or A is equal to, or A is equal to A is equal to 4R by root 2, that is 2 root 2 R. Okay, A is equal to 2 root 2 R. Now what is the volume of unit cell? Volume is AQ, or A means 2 root 2 R. So volume of unit cell is AQ, or 2 root 2 R whole cube. Okay, so now packing efficiency is volume occupied by 4 sphere, because 4 particles or 4 spheres present in the unit cell. So volume occupied by 4 sphere in the unit cell into 100 divided by total volume of the unit cell. So volume of one sphere is sphere is 4 third pi r cube. So volume of total 4 sphere is 4 into 4 third pi r cube divided by a cube. A cube means 2r whole cube into 100. So after calculation, it is seen that the packing efficiency of face centered cubic unit cell is 74%. So in face centered cubic unit cell, total 74% space is occupied, and the rest 26% volume is unoccupied, that is void space in face centered cubic unit cell. Similarly, in case of body centered cubic unit cell, body centered, you can see cubic unit cell, this picture is, this one is the picture. Okay, and remember that in case of body centered cubic unit cell, the particles are not attached along the edge diagonal of the along the edge length of unit cell, and also they are not attached along the phase diagonal of the unit cell. Okay, in case of body centered cubic unit cell, the particles are not attached along the side of the unit cell or along the phase diagonal of the unit cell. In case of body centered cubic unit cell, particles are attached along the body diagonal of the unit cell. According to this picture, this unit cell, the phase diagonal is AG or BH. These are phase diagonal, while the while the body diagonal is AF, not AE. AF. AF is the body diagonal. Okay, and in body centered cubic unit cell, the particles are attached along the body diagonal of the unit cell. Okay, now if edge length of unit cell is A, then body phase diagonal is root 2A, phase diagonal is root 2A, and body diagonal, that is AF, body diagonal AF is equal to root 3A. After calculation, it is seen that body diagonal AF is equal to root 3. So, and if the radius of each sphere is r, then you can also write r plus 2r plus r, that is r plus 2r plus r, that is 4r. 4r is also the body diagonal. Okay, 4r, in terms of radius of each sphere, the body diagonal is 4r, and if the edge of unit cell is a, then after calculation we can show the body diagonal is root 3a. So you can also write root 3a is equal to 4r. Okay, here this this sentence you have to remember that uh, the in body centered cubic unit cell the particles are attached along the body diagonal. Okay, so root 3a is equal to 4r in case of body centered cubic unit cell, or a is equal to 4r by root 3. A is equal to 4r by root 3, and volume of units volume of unit cell is a cube. So volume of the unit cell is a cube. A cube means 4r by root 3 whole cube, that is 4 4 4 by root 3 r to the power whole cube. This is the volume of unit cell, and in body centered unit cell the total 2 particles are present per unit cell. So volume of 2 sphere, volume of 1 sphere is 4/3 pi r cube. The volume of 2 sphere is 2 into 4/3 pi r cube. 2 into 4/3 pi r cube. This is the volume occupied by 2 particles, and this is the entire volume of the unit cell. So packing efficiency is volume occupied by 2 sphere in the unit cell into 100 divided by total volume of the unit cell. So after calculation you will get 68% volume is occupied in case of body centered cubic unit cell. Okay, and rest of 32% volume is unoccupied by the particles in body centered cubic unit cell. So from this calculation it is clear that in case of face centered cubic unit cell the maximum volume is occupied, that is 74% volume is occupied by the particles. Okay, that is in case of face centered cubic unit cell particles are most closely packed, and packing efficiency is maximum for face centered cubic unit cell and minimum for simple cubic unit cell. Okay, that is, see this table. In case of face centered, FCC means face centered cubic unit cell, face centered cubic unit cell. In case of face centered cubic, the packing efficiency is 74%. In case of body centered cubic, packing efficiency is 68%. In case of simple cubic, packing efficiency is 52.4, that is 52%. Okay, and now next topic is calculation of density in crystal system. Using a simple relation you can calculate the density of a unit cell. Density means mass per unit volume. So density of unit cell is the mass of unit cell by volume of unit cell. Okay, mass of unit cell. Now mass of unit cell, if there are z number of particles are present, z number of particles is present per unit cell, and mass of each unit cell, mass of each particle is m, then mass of unit cell is z into m. Okay, and volume of unit cell is a cube. So z into small m by a cube is the volume of unit cell. Now you can calculate mass of unit cell in term, you can convert the mass into molecular weight, okay, of the particles. If the so mass of unit cell is equal to m by na, molecular weight of the particles divided by Avogadro number. Okay, and after solving you will get this simple formula for calculation of density. The formula is density is equal to z into m by a cube into na. This is an important formula of calculation of density in unit cell, where d is density, z is number of particles per unit cell, that is Z is 1 for simple cubic unit cell, Z is 2 for body centered cubic unit cell, and Z is 4 for face centered cubic unit cell. And where A is the edge length of unit cell, and Na is the Avogadro number, and M is the atomic weight of the constituent particles. Using this simple formula, you have to calculate density, or you have to calculate atomic weight of the crystalline substance. Okay, or you have to calculate side or edge length A of the unit cell, and you have to calculate types of unit cell, that is you have to calculate Z atomic number of particles per unit cell. Okay, from this relation or formula, four value of four parameters will be given. Only one value of one parameter you have to calculate. Okay, two examples are given. First question, example number 1.4. X-ray diffraction studies show that copper crystallizes in phase FCC. FCC means phase centered, and in case of phase centered, you have to assume that Z is equal to 4. Okay, copper crystallizes in FCC unit cell with edge length is 3.608 into 10 to the minus 8 centimeter. So value of small a is 3.608 into 10 to the minus 8. Okay, so value of Z is given, value of A is given, and copper atomic calculate the atomic mass of copper, density also given, D is also given. So you have to calculate M. Okay, so M, we know that D is equal to Z into M by Na into AQ, and M is equal to dNa AQ divided by Z. So just put the value and you will get the value of M, that is atomic mass. And the atomic mass of copper will be 63.1. Very simple calculation using the formula of density calculation. Okay, similarly one more question. Silver forms a CCP crystal lattice. CCP means, you have to remember that CCP means face centered. CCP and FCC are same. Okay, so it is said that silver forms CCP lattice, that is face center lattice, that is value of Z is 4, and X-ray studies of this crystal show that the edge length of unit cell is 408.6. So value of A is 408.6 picometer. Here one thing you have to remember, that you have to convert picometer into centimeter by multiplying this value by 10 to the minus 8, 10 to the minus 10. Okay, and calculate the density of silver. Atomic mass of silver is given, value of M is given, you have to calculate value of D. Okay, since the lattice is CCP, that is FCC face centered, the number of silver atom per unit cell is 4, value of Z is 4, and molar mass of silver is M, value of capital M is 107.9 gram per mole. Okay, and edge length of unit cell is given 408.6 picometer, and it is converted into meter by multiplying 10 to the power minus 12. You can also convert it into centimeter. Okay, by multiplying by 10 to the minus 2. If you convert this 408.6 picometer into centimeter by multiplying 10 to the minus 10, then you have to take the value of density, this one, in CGS unit. And now just calculate by putting the values. So Z is equal to 4 and M is equal to 107.9 into 10 to the minus 3 kg per mole, and value of AQ is 408.6 into 10 to the minus 12 meter to the per cube, and Avogadro number, we know that value of Avogadro number is 6.022 into 10 to the minus 23. Now after calculation you will get the value 10.5 gram per centimeter. Such type of numerical, small numerical, you have to solve using the formula of density calculation, and you have to also practice calculation of packing efficiency in different types of crystal system or unit cell. Okay, and in next video I'll discuss about uh, I'll in next video I'll discuss about packing, different types of packing. That is one dimensional, two dimensional, three dimensional, closed packing. Okay, bye students.